All right, so I know you guys are probably disappointed that we're in here right now, but to be truthful, I'm not, because the more I can keep you and the other class together, the easier it is for me to keep like scheduling purposes in check. So we're going to continue talking about the derivative today. We're going to take a look at another way we can find a derivative using a limit. Just a little FYI, I know the limits can be a little bit involved. I hope that we're starting to get more familiar with them. But there is light at the end of the tunnel. Okay, in a few short sections, we're going to start talking about shortcuts to help us find derivatives, which I'm sure all of you would appreciate. Yes?
What page is up there?
This is page 97. 97, okay? So we're going to kind of break down two of the equations we've looked at so far in this equation, or in this section. One of them is the quadratic one, and then I believe we used the square root one kind of yesterday. And if you were to look back in your notes, we found that the derivative for the quadratic function was negative 2x minus 4. And if you were to look back in your notes from yesterday, the derivative for the square root was 1 over 2 times the square root of x plus 2. When I say derivative, you think what? Yeah.
Slope of tangent line.
Slope of tangent line. Slope at one point. Okay? You're used to finding slope between 2 points. Calculus is all about the slope at 1 point, aka a derivative. So these two equations that represent the slope at 1 point can be used to help you figure out that specific slope value. So for instance, let's maybe say our 1 point that we're interested in is x is negative 1.
Please excuse interruption. I need freshmen and sophomores to report to the auditorium. That's freshmen and sophomores to report to the auditorium.
Okay. So this derivative equation represents the slope at any point. If we wanted to check the slope at negative 1, we could simply plug in that location into our derivative. And looks like our slope value would be 2. So at that specific location on the graph, the slope of the tangent line is 2. You could go up 2 over 1 and draw your tangent line. Yeah. Sorry, negative 2. Yeah. Good check. All right, let's go ahead and try the other equation. Let's say for this particular graph, we were interested at the slope at 7. So we'll plug in 7 into our derivative equation. Let's see, square root of 9 is 3 times 2 is 6. So it looks like our slope at that location is 1/6. Okay, hopefully that's nothing really new to us yet. We used the limit definition yesterday to find those equations. And now that we have those equations, we can plug in any number we want. We're going to switch gears a bit, bless you, and take a look at what this limit might be representing. Do you see how it's kind of similar to the one we were using yesterday, but just slightly different? You notice how this one has a specific a value, whereas the derivative one from yesterday had an h in it. Okay, it's slightly different, but I just want to talk about where this limit is coming from. So I'm going to draw a little graph on the right-hand side over here, and we're going to analyze that kind of upside-down parabola shape that we did at the beginning of this section. If I were to pick a point and draw a tangent line, let's say I'm interested in figuring out the slope of that tangent line. And in this case, we're going to let this specific point have an x value of a. When we did this before, we labeled it as x. That way it could represent any point we wanted. But in this case, we're going to let it be a specific point we want. What might the ordered pair of that tangent point look like? Can we figure out what the x value and y value would be? What do you think, Ryan?
It would be a comma f of x.
f of x, in this case it would actually be a, because that's the x value we would plug in. Okay, so f of x typically means y, that's right, but we're going to plug in a, because that's the location. Okay. Now in our derivative analysis, we said that in order to figure out the derivative, okay, the slope of the tangent line, we had to first figure out a secant line and move that secant closer and closer to the tangent point. So we're going to pick another point on the curve. We don't know what this one is because we can let it be whatever we want. So we'll label that one as x, which means the ordered pair would look like x comma f of x. So let's draw a secant line through those 2 points. Do you guys notice if I let the x value get closer and closer to a, then this x point would become closer and closer to the a point, which means the secant line eventually becomes the tangent line. Isn't that the same concept we talked about a few days ago for a derivative? Okay, so it's still the same idea, just instead of letting us start at any x location, now we're starting at one that's kind of a point of interest for us. Okay, this specific location of a. So take a look at this limit. Notice how f of x is the y value from the one point, and f of a is the y value from the other one, and we are subtracting them together. Then we are dividing the x minus the a. Do you see how this is still slope? Y's over x's. Okay? So this is still the slope of the tangent line, but it's specifically at this location of a. It's no longer representing an equation that could let us find any point we wanted. It's now representing the slope at one point that we are really interested in. Okay, so we're going to take a look at how this limit, which still represents a derivative, it's still the slope of a tangent line, can help us figure out that slope value. So we're going to use this limit on these two equations to see what result we actually get. So let's check out the limit as x approaches a. Let's use the a value of -1. That was kind of a specific location we were interested in this middle column. So let's fill in the different pieces to this limit. The first piece that we see is f of x, which just represents the original equation. And then we have to subtract f of a. Now remember, a is that specific x location you're interested in, okay, this -1 value. So how might we find f of a? Yes?
From -1 for each of the x's in the original equation.
Yep, we're going to plug in,
Whatever the number is.
perfect. We're going to plug in -1 into the original equation to see what that number value would be. Looks like -1 plus 4 plus 1, which would just be 4. So f of a, in this case f of -1, would be a value of 4. So we're going to subtract that. And this is all over x minus a, meaning x minus -1, so that would change to a plus. So this is a different way to figure out the slope of a tangent line. Just in this case, we are only figuring out the slope at this -1 location, not necessarily at any point. Okay, so let's go ahead and simplify this limit. What do you guys feel like doing from there? Can we use some of our limit techniques? Factoring, conjugates, expansion, fraction work, any of the above? Yeah.
We can already tell that we were to substitute in because that's what we should do all the time.
Okay, so if you try,
Well, at least first.
at least first, if you try direct substitution first, what would happen?
Well, we'll get 0 on the bottom, so we know it's at least the asymptote.
And if you took the time to plug it in up top, you're going to get 0 again. Okay, so direct substitution is going to lead to 0 over 0, which means the limit does exist, so we should anticipate a number. We just have to do a little bit more work to figure out what that number is. You see something else? Yeah.
So we can combine like terms at the top because +1 and -4 are like terms.
All right.
-3.
-3, perfect.
And using that, since it's a quadratic, we can factor it.
Okay.
I believe.
So let's try to factor. Notice how the x squared, though, is negative. So we'll pull that negative out. And if we pull a negative out, that's going to change all the signs. So this would now be a +3 and a +4. Can we think of two numbers that multiplied a +3 and add to a +4? Yeah. X plus 3, x plus 1. Notice how x plus 1s will go away. So we're left with negative quantity x plus 3. And even though direct substitution didn't work at the beginning, because we got 0 over 0, let's try direct substitution now. -1 plus 3 is 2, but we have a negative out front, which would make it -2. So notice how we still get the same slope value as before. We just approached it from a different viewpoint. Instead of finding the derivative equation that represents the slope at any point and then plugging in -1, because that's the point you were interested in. You see how that's kind of a two-step process? Find the derivative equation and then plug in 1. Okay? You could simply use one limit that would lead you to the same result. Okay, so it's a different way of approaching it. Instead of finding a general derivative and then plugging in a number, you could simply use one limit that still represents the derivative, but it's only at this spot. Okay, because that's where we were interested in. Let's see if we can do the same thing for the other one. Let's anticipate a value of 1/6. So as x approaches, our special point of interest in this one was 7. Looking at the limit at the top, we're going to start with f of x, which is just the original equation. We then have to subtract f of 7. So if we plug in 7 into the original, looks like we get 3. And that's all over x minus 7. So since it's a limit, try direct substitution first. If you look at it kind of quickly, definitely 0 on the bottom, and if you thought about the top, you'd eventually get 0 as well. 0 over 0, we have a hole, which means the limit does exist. We just have to do a little bit more to figure that out. So think about your techniques for limits. Where do you want to go from there to help you evaluate it? Is there something in there that's kind of popping out as a little light bulb? Like what we need to do? What do you see? Yeah.
There's obviously things that there's a square root, so we can use conjugate.
Let's use
it. The top to be without a square root.
Perfect.
Be able to cancel it.
Wonderful.
On the bottom.
We're going to use a conjugate because there's a square root in that limit. Okay, so we're going to take that conjugate and multiply it up top, but also multiply it down below. Multiplying the conjugate up top, though, going through a FOIL process, the insides and outsides will always cancel each other out. So we just have to multiply the first terms and the last terms. Multiplied the first together, the square roots would cancel, so we're just left with x plus 2. And if we multiply the last, -3 times +3 would give us a -9. The denominator, though, will have x minus 7 times that conjugate. Where do you want to go from there? Do you notice anything? Good, Lauren? There you go. 2 minus 9 would lead us to a minus 7, which would match the x minus 7 in the denominator. So we have 1 over that conjugate. So notice how if we try direct substitution now, plugging in 7, 1 over 3 plus 3, which would be 6. So notice how the 1/6 is the same result. Okay, so this is an alternative definition. It's another limit we could use to help us find the derivative, the slope at one point. But notice how this one's a little bit more specific because you have to know a certain location at which you are trying to find that slope. If you don't know that location, you have to use the H limit that we were working on yesterday. Okay, this one only works if you know a specific spot. So we're going to make note of that. Okay, at the bottom, it's asking you what exactly does this limit represent. We'll say it represents the slope of the tangent line, aka derivative, at a specific location or point. Okay, you have some x value that you are trying to find the slope at. So it's slightly different than the one we were using yesterday. It's still a derivative, but it's just a different limit to help you find it. All right, so on the back of that page, just so we're clear on the two different limits we have, we're going to fill in what each one of them represents. Okay, we have the H limit from yesterday, and we have this new kind of A limit from today. They both represent slope, but it's how they find the slope is something different. So when you're using the H limit, your answer or result from this limit is usually an equation. Okay, there's an x value left over. For instance, if you look at the ones on the last page we did, we were left with an x in that derivative equation and an x left in this one. Okay, so the H limit is representing an equation that can be used to find the slope of the tangent line at any point. All right, it's kind of a generic equation. You can use that for any location. But let's say you were specifically interested in one spot graphically. Okay, maybe we could use this alternative definition. So if you take a look at what this limit gave us, okay, I'm going to flip to the other page. When we use this alternative limit, notice how we did not get an equation as the answer. Okay, we got a number as an answer, meaning a value. So it's something completely different here. The H limit gives us an equation, whereas the A limit gives us a value, okay, a number. And this number represents the slope of the tangent line at a specific point. Do we see the difference between the two limits? They're both representing slope, aka derivative. It's just, what are you trying to find? Are you trying to find a generic slope, meaning for any point graphically, or are you trying to find a specific slope at one location, and that's the only one you're really interested in? Okay, so they both mean slope, they both mean derivative. It's just, what are you interested in finding? Okay, we're going to explore the differences between these two limits a little bit more, okay? But for right now, we just got to understand what they each represent, okay? All right, so we are going to switch gears and we're going to take a look at what the derivative means graphically. I think we're going to like this a little bit more than the limit stuff because we're looking at pictures. So do me a favor and go ahead and turn to page 101. This is the beginning of our next section. So far we've said that a derivative represents the slope of a tangent line drawn at any point. Okay, that's kind of the first sentence at the top of that page. Let's get this in here. All right, so the derivative represents the slope of a tangent line at any point. We're going to use that idea to complete this table below to estimate, okay, approximately find the derivative at certain locations. Okay, so take a look. Our first location graphically is the x value of -7. So if you were to go to this graph, 1, 2, 3, 4, 5, 6, 7, notice how you would be talking about this point right there. Okay? If you were to draw as accurately as possible a tangent line at that point, okay, only touching once, go ahead and try to draw that in, maybe lightly on your paper. We're going to estimate what that slope is roughly. So in terms of notation, we'll say f prime of -7. Okay, the derivative or the slope at that point is approximately, little squiggles, some number. So after you draw your tangent line, I want you to find another really good point somewhere on that line. Looks like I have one right there. And can you calculate the slope between those 2 points? What is the slope of that red tangent line? Can you figure out rise over run? What does it look like it is roughly? Yeah.
Rise 5 over 1 run.
Okay.
So basically 5.
5, basically 5, okay? Depending on how you drew yours, maybe yours was about 4, okay? Remember, this is just an estimation, okay? So we're drawing a tangent line as best we can. We're going to find 2 points on that line and try to calculate or estimate the slope, okay? Let's take a look at this one. Is the function, okay, meaning the black original graph, increasing, decreasing, or at a max or minimum at this location? Okay, we're looking at this point of -7, or x location of -7 on the graph. What do you think?
It is increasing.
How do you know?
Because from the left side to the right side of the graph, it is going up.
Perfect.
Towards the relative maximum.
Towards a max, okay. If you were to trace this graph with your pencil, okay, wouldn't your pencil at this point be traveling upward, aka increasing? Okay, so at that spot our pencil would be going up. We can say it's increasing there. Let's go ahead and now try to figure out what the equation of this tangent line might be. What information do you need to know to write the equation of a line? Yeah. A point and a slope. Okay? So let's go ahead and try to figure this out. If we were to plug in this x value of -7 into the original equation, aka f of x, aka y, what height would we get out? Can you tell based off the graph? Yeah.
We would get -8.
-3. So the height of this point in terms of the y-axis is -3. If we were to take a look at the slope at this point, we said the slope, aka derivative at -7, was roughly 5. So we got to put those two pieces together to write our equation of a line. You can leave it in point slope form if you want to. So if we did that, we would have y plus 3 equals 5 times x plus 7. So there's the equation of that red tangent line we drew specifically at this location. Okay, we're going to repeat the process for some of these other points. So let's go ahead and check out -6. That's this point on the black graph. If you were to try to the best of your ability to draw a tangent line only touching once, can we estimate about what the slope is at that point? Go ahead and try to find another good point on the graph. Looks like I have one there, maybe. Remember, this is just an estimate, roughly. 2, I'd say, sure. Okay, sure. If you were tracing this graph and you were to reach this spot, notice how your pen or pencil would be going up. So we are increasing at that location. Let's see if we can figure out the equation of that red tangent line. If we were to plug in -6 into the graph, the point value, aka y value, would be 0. We're on the x-axis. If we were to analyze the slope, aka derivative at that point, we said that was roughly 2. So with that point and with that slope, you can write your equation. Y minus 0 equals 2 times x plus 6. We doing okay so far? Do you guys think you can do a few more on your own? Yeah? Okay. Go ahead and try -4. Any takers for the slope estimation? Notice how your tangent line is flat. What do you think, Josh?
So none?
None, aka 0. Do you have are you increasing, decreasing, max, or min at that spot? Yeah.
Relative max.
We have a max, yep. Alright, so let's check out the point and the slope for the equation. If you plugged in -4 into the graph, it looks like the point value would be 2, height of 2, and you said the slope at that point was flat or no slope, aka 0. So our equation, y minus 2 equals 0 times x plus 4. How'd you guys do? Pretty good? All right, let's go on to the next one. We have -2. Go ahead and try to draw a tangent line, only touching once. Bless you. Based off your tangent line, can we estimate what the slope is about? Can you find another good point on your line to calculate rise over run? Yeah?
I found it to be about -1.
About -1. I think that's right. Increasing, decreasing, max or min at this spot? If you're tracing it with your pencil, what would your pencil be doing?
Decrease.
We're going down, yep, so we're decreasing. Let's check out the point at -2 and the slope at -2 for our equation. Based off the graph, the point value is 1. We estimated the slope to be -1. So writing our equation, y minus 1 equals -1 times x plus 2. Am I going too fast? Pretty good? Alright, let's check out our next one. X value of -1, that's our next point. This one's a little tricky to draw a tangent line. Only touching that spot. Can we estimate the slope? Find another good point on your line, rise over run. Let's see. Yeah?
Funny enough, I was thinking it was going to be the point that we were just talking about, -2 on.
It probably, yeah, kind of looks like that. I would say roughly -2. Yeah, -2. Alright, if we were tracing the graph at that spot, our pencil would be going down, so we're decreasing. And if we check out the point and slope at this -1 location, the point value is -1. We estimated the slope to be -2. So equation comes, we have y plus 1 equals -2 times x plus 1. Alright, next location, x value of 1. Draw a tangent line, only touching once. What's the slope of that flat line? That horizontal line? Yeah.
0.
We got 0. Increasing, decreasing, max or min? Yeah.
Relative minimum.
We have a minimum. Good. Alright, so let's see. The point at 1 and the slope at 1. We need those to write our equation. Point value looks like -4. Slope value we said was 0 based off that derivative estimation. So we have y plus 4 equals 0 times x minus 1. We getting in the groove? Okay. Let's check out our next point, x location of 3. Try your best to draw a tangent line. Roughly, what is that slope about? Does yours look like about 3 maybe? Up 3 over 1? Close to that? Okay, so we'll say our estimation is 3. If we were tracing the graph, our pencil would be going up at that location. So we are increasing. Let's see, the point on the graph at 3 has a height of -1. Slope of the graph at 3 we said was 3. Bringing those together, y plus 1 equals 3 times x minus 3. Can you guys try the last two on your own? Okay. Go ahead and check out the x location of 5 and the x location of 7. Any takers on the 5 location? Derivative, aka slope estimation, increasing, decreasing max or min in the equation? Brave soul. Go, Brianna? Zero, okay. Perfect. All right. Yep. Perfect. How'd you do? Good? All right, last one. Taker for 7. What was your slope roughly? I know it's an estimation, so maybe not everyone has the same. What'd you get? Yeah. -4. Okay. Decreasing.
Point is after 7 and is -1.
Yep.
So we went over -4, and the equation is -1 equals -4 times the equation.
Really good. All right. We'll check out that last one tomorrow. Good job today, guys.